So the final type of proof by inductions that you might have to do are recurrence relation proofs. You've met recurrence relations in the A2 single maths series pack. And a recurrence relation is just a formula to generate a sequence based on the previous terms in the sequence. You need the recurrence relation here and the first term of the recurrence relation to be able to generate the rest of them. It turns out that you can write these as an nth term formula as well. And what we're going to do here is just work out the first 5 terms to show that they are the same, but then we're going to prove this by induction for all positive integer n's. So finding the first 5 terms of this sequence. So u1 is given in the question to be 1. Then u2 is 3 times u1 plus 4. So that's 3 times 1 plus 4, which is 7. And we can generate the rest of our terms from here. So u3 is 3u2 plus 4. That's 3 times 7 plus 4, which is 25. u4 is 3u3 plus 4. That's 3 times 25 plus 4, which is 79. And your 5th term, u5, is 3u4 plus 4, which is 3 times 79 plus 4, which is 241. Generating the first 5 terms for the nth term, we're just going to sub in n is 1, n is 2, n is 3, and so on. So u1 is 3 to the 1 minus 2, which is 1, so that one's correct. u2 is 3 squared minus 2, which is 9 minus 2, which is 7, which works. u3 is 3 cubed minus 2, so it's 27 minus 2, which is 25. That's right. u4 is 3 to the 4 minus 2, which is 81 minus 2. That's 79, which is correct. And then u5, that's 3 to the 5 minus 2, it's 243 minus 2, which is 24. So we show that this works for the first 5 terms. This isn't enough to prove that these 2 things are the same because we don't know what happens after that. So to prove that these 2 things are the same, we need to use induction. Now we start very similarly, but it is different for recurrence relations and nth term formulas. One of the big things is what happens with n. So if you say consider n equals 1, if you put n equals 1 into your nth term formula, you get u1, work out u1. But if you put n equals 1 into your recurrence relation, you get u2 instead. So it's a little bit weird talking about n equals 1, n equals 2, and so on. Instead, I'm going to consider u1 first. Now, if we consider u1 from the recurrence relation, we're told that u1 is 1. And if we put in 1 into our nth term formula, we get that u1 is 1, which is right. But all you've done here is show that the first term is correct. You haven't shown anything about the recurrence relation. So one of the things for a recurrence relation proof is that you must also consider u2. So you've got to start by considering 2 values. From the recurrence relation, u2 is 3, u1 plus 4. We know u1 is 1, so this is 7. From the nth term formula, u2 is 3 squared minus 2, which is 7. So it does work. I'm going to put so the statement is true for u1 and u2. Next comes our assumption step. So we assume that it's true for uk, which is that uk equals 3 to the k minus 2. And then we consider uk plus 1. What we're aiming to get is the nth term. So we're aiming to show that if we sub k is 1 into the nth term, that's true. And we're going to get that by starting off from the recurrence relation. So the recurrence relation says that uk plus 1 equals 3 uk plus 1. We've assumed earlier on in the question that uk is equal to 3 to the k minus 2, so I can substitute that in. And then if I expand this out, 6 plus 4, 3 times 3 to the k gives you 3 to the k plus 1. Minus 6 plus 4 gives you minus 2, which was our aim. Tie this up at the end. Further statement. uk plus 1. And then finally, your conclusion. So, if true for uk, then we have shown it to be true for UK plus 1, as true for U1 and U2 by induction, true for all n in the positive integers. Now, the final example I think is unlikely to come up in your exam, but just in case it does. This is a recurrence relation that's based on the previous 2 terms rather than the previous 10. So in this one, you get given the first 2 terms and you get given the recurrence relation here, and we're asked to prove this entity. Start off with, we must consider U1 to show that the first term works, U2 to show that the second term works, and to show that one of the recurrence relation terms works, we have to consider U3 as well. U1 equals 13. From the nth term, this is 2 to the 1 plus 1 plus 3 to the 1 plus 1. That's 2 squared plus 3 squared, so 4 plus 9, which equals 13. That's true. U2 is 35 from the nth term formula. That's 2 to the 2 plus 1 plus 3 to the 2 plus 1. And that's 2 cubed plus 3 cubed. So that's 8 plus 27, which is 35. That works. And finally, we have to show that it works for U3. Now, from the recurrence relation, U3 is 5U2 minus 6U1. That's 5 times 35 minus 6 times 13, which is 97. From the nth term, this is 2 to the 3 plus 1 plus 3 to the 3 plus 1, 2 to the 4 plus 3 to the 4. That's 16 plus 81, which does equal 97. So it's true for U1, U2, and U3. Now, in your assumption step, we assume that it's true for n equals k. So that's assuming that UK equals 2 to the k plus 1 plus 3 to the k plus 1. And we must also assume that it's true for n equals k plus 1, because our recurrence relation is based on the previous 2 terms. So, and true for UK plus 1. So, and we've got UK plus 1 equals 2 to the k plus 2 plus 3 to the k plus 2. So now we consider n equals k plus 2, or UK plus 2. So I'm aiming to show that UK plus 2 is equal to the k plus 3 plus 3 to the k plus 3. That's subbing in k plus 2 into my nth term formula. From my recurrence relation, UK plus 2 equals 5 UK plus 1 minus 6 UK, and I can put my assumption steps into here. So 5 times 2 to the k plus 2 plus 3 to the k plus 2 minus 6 times 2 to the k plus 1 plus 3 to the k plus 1. I'm going to expand these out and collect my 2's and 3's up together. So I've got 5 times 2 to the k plus 2 minus 6 times 2 to the k plus 1. Collecting my 3's up, I've got 5 times 3 to the k plus 2 minus 6 times 3 to the k plus 1. I need to write these powers, these 2's and 3's of the same power. So I'm going to go for the lowest power of these, or the like 2 to the k would work and stuff as well. So I want to write these as 2 to the k plus 1. The 2 to the k plus 2, I can write as 2 times 2 to the k plus 1. And this is 10 lots of 2 to the k plus 1. Minus 6 lots of 2 to the k plus 1. Overall, that gives me 4 lots of 2 to the k plus 1. 4 is 2 squared, and I can add those powers to give 2 to the k plus 3. Doing the same on the 3's, so I can write 3 to the k plus 2 as 3 times 3 to the k plus 1. 3 times 5 is 15, so I've got 15 lots minus 6 lots, which gives me 9 lots of 3 to the k plus 1. 9 is 3 squared, and I add those powers and give me 3 to the k plus 3, which is our n. We've got 2 to the k plus 3 plus 3 to the k plus 3. Tie it up at the end and write your conclusion out, and that's that one done.